When we talk about electrochemical cells, what really do we mean? As we can see, it is the opposite of electrolytic cells. In electrolytic cells, when we talk about electrolysis and Faraday's law, we saw that the anode is positively charged and the cathode is negatively charged. Now, when we're talking about electrolytic cells, electrochemical cells, they are cells that have the anode to be negatively charged and the cathode to be positively charged. And we can see here they literally will make use of electrodes of different type, not of the same type, as we can see in electrolytic cells. So what are electrochemical cells? They are simply cells or devices that are known to convert chemical energy to electrical energy. Electrochemical cells simply consist of two half cells with electrodes dipped in their electrolytes, and these electrolytes are connected by a salt bridge, thus creating a potential difference between the two half cells, as we can see displayed. The reaction that is taking place in an electrochemical cell is simply redox reaction, as electrons are observed to be generated from the anode and migrates to the cathode, thereby creating a flow of electrons or electric current through these half cells, because a difference in potential between the electrodes have been generated. Now, talking about the creation of potential difference between the electrodes, we should get to see how an electrode can actually generate a potential between itself and the electrolyte. So, talking about potential difference, it is observed that when a metal is dipped in a solution of its salt, for example, when we dip zinc metal in a solution of zinc sulfate, it is observed that the zinc atoms in the zinc rod will give up their electrons, and go into the solution as zinc ions, thereby making the zinc metal to be negatively charged, while the solution, that is the electrolyte, now becomes positively charged. And when this happens, it is said to have created a potential between the zinc plate and the zinc electrolyte solution. That's the zinc salt solution. And this is what we call electropotential for zinc. Talking about what we just said now, this is actually what we are saying. The diagram illustrates better what we just talked about. So when a zinc rod is dipped into a solution of its salt, we observe that the zinc atoms in the rod will go into the solution as zinc ions, while they leave behind excess electrons on the zinc rod, and thus making the zinc rod to be negatively charged and the solution will be positively charged. So this difference in charges, or the difference in the polarity of the solution and the rod, creates that potential called electropotential for zinc. In similar manner, copper is also observed to create such electropotential when copper rod is dipped into its solution like copper 2 sulfate. It is observed here that the copper 2 ions in the solution this time around, not from the copper rod but from the solution, the electrolyte solution, will all migrate to receive electrons at the copper rod and gets deposited on the rod as copper atoms, thereby making the rod to be more positive while the solution will be negative. And as this happens, it creates a kind of potential between the rod and the electrolyte, which is called electropotential for copper. So this is actually what is observed when these rods are dipped into their electrolyte solutions. Now, having seen how electropotential can be generated between a rod and its solution, we shall talk about the standard condition for which this can happen, and that is referred to as standard electropotential. So when we talk about the standard electropotential, is simply that ideal condition for which the electropotential of a given metal, ion, and metal solid system can be generated. That is, when we dip the metal in its solution, that potential that will be generated can be generated in an ideal kind of condition. And what are these conditions, or what is this condition? We are talking about a temperature of 298 Kelvin, which is room temperature, that's 25 degrees Celsius, and the solution must be 1 molar or 1 mole per dm cube. So the standard electropotential for zinc and copper, as we can see displayed, is 1.1 volt. That is to say, when they are both used in a cell, in an electrochemical cell, it generates a voltage of 1.1 volt, and under ideal or standard condition of 298 Kelvin and 1 mole per dm cube, that's 1 molar. In a given cell made of zinc and copper, electrons will normally flow from the zinc rod to the copper rod because it is at a lower potential. But current will flow the other way around, that is from copper to zinc. So this is actually how electricity is generated. And talking about using copper and zinc as electrodes in a given electrochemical cell, it is worthy to note here that the slash, that is the stroke sign between zinc and the zinc atom and zinc ion, as we can see displayed on the screen, is simply the phase change. But the double strokes between zinc and copper is the salt bridge. So this is actually simply telling us that zinc has been oxidized from zinc 0 oxidation state to zinc 2 plus oxidation state, while copper has been reduced from copper 2 plus oxidation state to copper 0 oxidation state. So this is actually how electrodes are used in a given electrochemical cell or being represented. Now, this is for zinc and copper. In the case of zinc and copper, zinc becomes the anode, and electrons moves from the anode to the cathode, which is copper. And we have said that this happens so because zinc is at a lower potential to copper. But if we now use copper electrode and silver, what becomes of the electrochemical cell? What becomes of the electrochemical cell if copper and silver are to be used is that the copper rod becomes the anode this time, which is the negatively charged electrode, and that is where oxidation takes place, while the silver rod becomes the cathode, where reduction takes place, and that is the positive charge, that is a positive electrode. Thus, electrons will always flow from copper to silver, while current will flow the other way around. So we can see, and if that happens, we'll always see that according to the electropotential value for copper and silver, the overall potential for copper and silver will therefore be 0.46 volts. So that tells us that copper has been oxidized while silver has been reduced. So we shall get to see how to calculate the EMF of a given cell as we proceed down into the discussion. Now, talking about still the electropotential of cells, we shall be looking at what is called She. She is standard hydrogen electrode. What is She? It is simply a system that is used to compare the potential values of different metals dipped in their solution. So, the She simply consists of hydrogen gas at temperature of 298 Kelvin, that's room temperature, and of course a pressure of 1 atm, which is around an inert electrode. The electrode here in question is platinum electrode. So this is actually how the She system is designed. It's made up of platinum electrode, and of course we have a pressure of 1 atmosphere and a hydrogen gas at 298 Kelvin. So this is actually how the She device is constructed. So we can have example, as we can see here, example 1, we are looking at a cell is constructed by connecting zinc rod to She. So we are told to write the half cell reaction, the overall reaction, to find the electropotential, and then of course determine the direction of flow of the electrochemical cell, the direction of flow of electrons. So the electropotential for zinc we've been given as negative 0.76 volts, and this is actually what is happening there. So we can see that when the zinc plate or rod is connected to the standard hydrogen electrode She, electrons will usually flow from zinc rod to the She. So as electrons flow, the voltmeter will always read a value of 0.76 volts. That is actually what happens there. So we can see the connection between zinc and She. So looking at the connection between zinc and She, since electrons leaves zinc, it means that zinc loses electrons, and that is oxidation. So since zinc loses electron oxidation, it means at the hydrogen side, these electrons will be gained. So hydrogen will gain electrons, and that is reduction. So the overall reaction is zinc reacting with hydrogen ion to give us zinc plus and hydrogen gas liberated. So that tells us that zinc has been oxidized. So if we are to calculate the electropotential for that system, is simply going to be the electropotential at the right hand side minus electropotential of left hand side, or we can say electrode of reduction minus electrode of oxidation, and reduction is hydrogen, which is 0.00 minus 0.76, and that gives us positive 0.76 for zinc. So it tells us that the zinc is simply losing electrons, which made it to be the oxidation half cell reaction. So this is the relationship between a given metal ion system and She. So having seen that, I would like to test you, dear students, with the following classwork. So you can pause now, pause the video and attempt this question to put yourself in line with what we are doing, so that you can get used to calculating this type of questions. And after the classwork, you can proceed with this STS before continuing the class. Okay, so with that now, we shall now look at our next subtopic, that is standard electrode potential, which we've talked about. I want to see it more. So we're looking at standard electrode potential. So what do we mean by standard electrode potential? Look at the name, standard electrode potential. This is simply the measure of the ability of a metal ion to accept electrons and become the oxidizing agent. That is what we refer to as standard electrode potential. It's simply the measure of the ability of any metal ion system to accept electrons. That is what standard electrode potential is. We shall be talking more about this. So, but before then, let's take a brief look at the similarities between electrochemical cells and an electrolytic cell, so that we'll remind ourselves of what they are. So what are the similarities between electrochemical cells and electrolytic cells? In both cells, the oxidation takes place at the anode, while reduction takes place at the cathode, because at the anode, electrons are lost, while at the cathode, electrons are gained. That is one similarity between these two types of cells. Then we also know that electrons will always flow from the anode to the cathode in both types of cells. Electrons will always flow from anode to cathode, but currents will flow the opposite way. So let's take note of that. So these are the similarities between these two types of cells. So having seen the similarities, we can also talk about their differences. So like we said from the beginning of the discussion under electrochemical cells, we said that electrochemical cells have negative anode, but in the case of electrolytic cell, the anode is positive. So if anode is positive for electrolytic cell and negative for electrochemical cell, it means the cathode will be the opposite. So cathode is negative for electrolytic, but positive for electrochemical. Now, when we talk about the types of electrodes that are used, in the case of electrolytic cells, the same electrodes can be used. The same electrodes can be used to generate, to allow the flow of electricity into the electrolyte. Either the same electrodes or different electrodes. But for electrochemical cells, the electrodes must be different. Not just different, but with different potential values, so that we can have the flow of voltage, the flow of electric current, and the voltage can be supplied. So that is in terms of electrodes. Now, in terms of the conversion of energy, electrolytic cells simply converts electrical energy to chemical energy, but electrochemical cells is the other way around. They convert chemical energy to electrical energy. So that is actually what we should note. So that is the difference between electrolytic cells and electrochemical cells. So with that now, we shall be looking at EMF. What is the EMF of a given cell?